Hello. In the previous lecture, we had talked about how to convert a given context-free grammar into an equivalent PDA. Now let's work on the other direction, opposite direction, basically going from PDA to equivalent CFG. In other words, can we come up with a conversion algorithm such that given a push-down automata, the algorithm converts the push-down automata into an equivalent context-free grammar. So this direction is slightly harder or slightly complicated than the first direction. What we'll do is we'll first do some assumptions regarding the PDA that we are working with. Let's write down our assumptions. One is that let's assume that our PDA has a single accept state. For each of the assumptions that we list in here, we will need to show that we don't lose anything from the generality of our conversion algorithm. So basically, for instance, for this assumption, assuming that single accepting state, it's easy to show that even if a given PDA doesn't satisfy this assumption, we can easily convert it to an equivalent PDA that satisfies it. If a given PDA has multiple accepting states, for instance, in the following format, let's say this represents our PDA. If it has multiple accept states like this one, let's say we have 3 accept states, we can turn this into an equivalent PDA where we make these accepting states into non-accept states and introduce a new accepting state and simply make epsilon transitions from the previous accepting states into the new accepting state. So basically, by making this assumption, we don't lose anything from the generality of our claim. Secondly, we can again safely make the following second assumption, that stack is empty at accept. So basically, assuming we have a single accepting state, we can also assume that the stack is completely empty at the accepting state. Imagine that some PDA doesn't satisfy this requirement. We can again easily convert such a PDA into an equivalent PDA that satisfies this. How we could do that? Once we arrive at the accepting state of the PDA not satisfying this, we can simply say make this non-accept, introduce a new accepting state, and in that accepting state we can easily make a loop where we don't process any input from any symbol from the input string, and we keep on popping whatever symbol exists in the stack. And at the end, we could arrive at the accept state that where the stack is empty. And for the third assumption, let's see what the third assumption is. Let's assume that each transition in our PDA is either a push or a pop. Each transition is either a push or a pop, but not both of them. Again, so note that in most of the example PDAs that we had seen so far, those example PDAs were by themselves satisfying these two constraints. But some of them, it could be the case that doesn't satisfy this. But again, this by making this assumption, we don't lose anything from generality. Any given PDA that doesn't satisfy this can easily be converted into a PDA that satisfies this. How? Let's say we have a transition of the following form, A, B, C, that takes us from state I to state J in a given PDA that doesn't satisfy this condition. We can introduce the transitions equivalent to the single transition by the following. Note that in this transition we do both popping from the stack, popping B, and also pushing a symbol into the stack at the same time. With our new assumption, we don't want this, but we can satisfy such a constraint by having an equivalent PDA as follows. From the state I, keep a transition that reads the input symbol A and that pops B but not pushes anything, goes to an intermediate artificial state, let's call this R, and then from R to our original state J, we go through a transition where we don't read anything from the input symbol, we don't pop anything from the stack, but we simply push the symbol that we originally wanted to push with this transition. Note that these two transitions are now equivalent to this single transition, and these two transitions satisfy our assumption. So this is one case that would be against such an assumption. Another case could be that the transition could neither introduce a push nor a pop. So let's see how we could handle such transitions. So it could be that the case that our transition is as follows. We read A from the input, we don't pop anything, we don't push anything into the stack. Again, we can turn such a transition into equivalent transitions that satisfy this requirement, and that is equivalent to the single transition. We could do that by, let's say this is our original state I. In our first transition, we can simply push an artificial symbol, so A from the input string, don't pop anything from the stack, and push an artificial symbol, let's call it T, into the stack, go to an artificially introduced new state R, and from this R to our original state J, we can go through a transition that doesn't read anything from the input string and that pops the previously pushed artificial symbol T and doesn't push anything new into the stack. Note again that these two transitions, each one of them satisfies this constraint that every transition is either a push or a pop. The first one is push and doesn't pop anything, and the second one is a pop and doesn't push anything. So these two satisfy the assumption, the criteria that we want, and together they are equivalent to the original transition that we're not originally satisfying this given assumption. So this means that we can safely assume that all these three conditions hold regarding the PDA that we want to work with. Assuming now the PDA that we want to work with has all these constraints, how do we turn that PDA into an equivalent context-free grammar? The main idea that we will use is going to be as follows. From the PDA, taking a look at any pair of states, Qi and Qj, so let's say we take a look at some state Qi in our PDA and some state Qj in the PDA. Now there will be obviously in our PDA there will be many transitions that take us from Qi to Qj. Let's say that this is such a computation path that takes us from Qi to Qj. Now, if we can write a variable, let's call it Aij, if we can write a variable that corresponds to a variable in a grammar such that this variable generates all possible strings, input strings that are consumed by this part of our computation path in our PDA, then we can somehow simulate the given PDA using our context-free grammar. So basically we want to be able to create Aij such that Aij generates all possible strings consumed by the computation path from Qi to Qj in our PDA. Consumed by any computation path from Qi to Qj. Note that if we are able to do this, but there's one more thing we need to add in here, is that Aij should be able to generate all possible strings that are consumed by any computation path in here, assuming that we start at empty stack at Qi and we finish at empty stack Qj. Assuming we start with empty stack at Qi and finish with empty stack at Qj. If we are able to do this for every possible pair Qi, Qj of states in our PDA, then naturally we will be able to do the same thing for our starting state and the accepting state as well. So if we can do this, we will be able to find a, let's call this starting state as 1 or S, and let's call the accepting state A as well. Now we will have arrived at the variable ASA, so that ASA will be capable of generating all possible strings consumed by any computation path from the state QS, our starting state, QS starting state, and our accepting state QA, assuming that we start with empty stack at QS and we finish with empty stack at QA. ASA will correspond to all strings accepted by the given grammar. By the given PDA. Okay, so this is our general goal for every possible pair. This is what we want to do. We want to basically create a variable that corresponds to it, that corresponds to all strings that will be consumed by a computation path from Qi to Qj, assuming empty stack at the start and empty stack at the end. Now the important part will be how to do this. We will use the idea of induction to be able to do this. So the main idea is as follows. Let's try to see how a computation path from a given Qi, state Qi, to a state Qj might look like. Okay. Now remember, we said that we want to create Aij so that it will correspond to a string consumed in here, assuming empty stack at Qi and assuming empty stack at Qj. Since we are assuming empty stack at Qi, and since we have, remember our earlier 3 assumptions that we have made, that every transition is either a push or a pop. So we start at empty stack in here, then the only possibility for this transition, if every transition is to be either a push or a pop, is that this transition must be a push operation. So this transition will look like something like the following transition: A epsilon T, where A is the input symbol that is consumed, epsilon is popped, and T is pushed. Okay, since we are assuming that we are starting with empty stack at Qi, the initial transition in our computation path must be a push. It must be some transition of the following form, And similarly, since we assume that at Qj we end up with the empty stack in here, it must definitely be the case that this final transition in our computation path must be a pop, because every transition is either a push or a pop. This cannot be a further push, because we are assuming that at Qj, at the end of this computation path, we arrive at an empty stack. So this final transition, A, B, this is the input symbol that is consumed. It doesn't have to be the same as the input symbol consumed in here. B and T and epsilon. Some some pop in here. So initial transition is a push. Final transition on this computation path is a pop. Obviously, the type of the symbol that is pushed in here, basically T, must be the same as the type of the symbol that is popped at the end. So if it's a 0, 0 must be pushed in here, 0 must be popped in here. But that doesn't necessarily mean that the exact symbol itself that is pushed in here into the stack is exactly the same as the instance or the exact same symbol that is popped at the end, although they correspond to the same type of a symbol. Okay, so in this case we need to make a differentiation between two possible cases. One case is that it could be that after this initial transition until the final transition, in between in our computation path, stack may never get empty. Stack is never empty. So we push some symbol and then we did some work with our stack and taking some transitions, and before the final transition the stack never becomes completely empty, which means that exactly the symbol that we have pushed at the beginning in the first transition must correspond to the exact same symbol, the exact same physical symbol that we pop at the end as well. So this T that we push in here is exactly the same T that we pop at the end. This is one case, and corresponding to this case, actually we can easily now write our variable aij that will generate all possible strings that are consumed through this path. So corresponding to this case, we will write down a rule that says aij will generate. Now, after this transition, assume that qi is taken to some state, call it qr, and right before the final transition, assume that we are at some state qs. Now, by inductive hypothesis, we can assume that we are able to generate all such strings that correspond to strings generated for shorter computation paths. Now, what we have in here is we have a shorter computation path that starts at state qr and that finishes at state qs, and at qr we can assume the stack is empty, forgetting about the first push symbol, and at qs we can assume that the stack is empty, forgetting about the last popped symbol, because the stack in between qr and qs never gets empty throughout our computations. So we can write our variable ars to correspond to all strings that are generated through the computation path in between qr and qs. We finally need to add the input symbol that we have consumed with the first transition, which is a, and then followed by ars, the strings that are generated via the variable ars. And finally, the final transition consumes the input symbol b. We can write it at the end of ars. So aij corresponds to all such strings where in the input string it starts with an a, and then all strings generated through the variable ARS followed by a symbol B in our input string. So this is case 1. For case 1, we have been able to write down a rule corresponding to our variable aij, which will correspond to all strings consumed through a computation path starting at qi with empty stack and ending at state qj with empty stack. The second case is that in between qr and qs in here, the stack might get empty. So it could be the case that this symbol T that we push in here, basically we take some transitions in here, and in between somewhere here, this physical symbol C itself is popped at the end and the stack became empty in here. But then again, maybe we have pushed that symbol, that type of a symbol again, and at the end that is removed again. So it could be the case that the stack may become empty somewhere in this path as well. So that's the second case, qi, and this is our initial transition, a epsilon t, and then this is our final transition, qj and bt epsilon. Now corresponding to this case, we said that the stack might have become empty somewhere in the middle, let's say at some state qr. So this corresponds to the case where stack may become empty at some state qr. Now how do we handle this case? How do we basically write down rules corresponding to our variable aij for this case? Now again, we can use the principles of induction. We will try to write a rule so that we can generate aij, the strings corresponding to aij, from smaller strings where we have been able to write down rules for the corresponding variables. Now let's look at our figure. According to this figure, we start with empty stack at qi, and the stack becomes empty at some intermediate state qr as well, qr. So to be able to generate the string corresponding to the whole path, now we can split it into two parts. One part will basically be the part of the path that goes from qi all the way until qr. So aij in this case can be generated through two variables. The first variable will be air. Note that air, according to our inductive hypothesis, is able to generate all strings that correspond to the strings consumed in the path from qi to qr, assuming qi, when we start at qi, the stack is empty and the stack is empty at qr. Okay, so air will generate all such strings consumed in this path. We can do the same thing from the second part of the path that starts at qr and that goes all the way until qj through our variable arj. In this case, again, note that the stack is empty at the beginning of our at the initial state qr, and it's also assumed that the stack is empty at qj, and arj then can generate any string that is consumed through this path starting at qr and ending at qj. So these are all the two possible cases, that in between the computation path from qi to qj, stack is never empty. If that's the case, we can write down rules of this form. and the second case, in between this path, the stack may become empty at some state. If that's the case, then we can generate Aij by splitting it into two smaller paths and writing down two variables corresponding to strings generated on those two smaller, shorter paths, AIR and ARJ. And finally, so this is the inductive part of our conversion algorithm, and for the base case of our conversion algorithm, and introduce AII going to epsilon for every possible I. This will correspond to the base case of our construction, because going from a state Qi to a state Qi, we can easily consume just the empty string and arrive at, starting at Qi, arrive at Qi. Okay, so this will basically correspond to saying that by just in the computation path from Qi to Qi, only epsilon is consumed. Now, if we can apply this for this overall construction for every possible pair Ij, then at the end, the variable that corresponds to ARS, where ASA, so variable ASA, where S is our starting state, S is starting state, and A is our accepting state of our PDA. This variable ASA will be the starting variable of our context-free grammar that simulates our PDA. Basically, the context-free grammar that we come up with will be able to generate all the strings that are accepted by the given PDA and will reject anything else. Let's see how this construction works on a specific example to make things more concrete. An example conversion from a given PDA into an equivalent context-free grammar. This is our, let's say this is our input PDA. Initial starting state is 1, a transition epsilon epsilon dollar into a state, let's call it 2, and at state 2 we have a loop on two transitions, 0 epsilon 0 and 1 0 epsilon, and it has a transition into our accepting state, let's call it 3, or the following transition epsilon dollar epsilon. This is our input PDA, and we want to convert this PDA into an equivalent context-free grammar by applying the conversion algorithm that we just discussed. Let's first make sure that the three assumptions that we make regarding our PDA hold. If any of them doesn't hold, then we can apply the operations that we described to modify the PDA such that we get an equivalent PDA and it satisfies the given constraints. So one of the constraints was that we have to have a single accepting state. So for this PDA, we don't need to do any modifications because it already contains a single PDA. And a second condition was that our PDA should accept with the empty stack. Let's see if that's satisfied with our specific PDA. The first transition of our specific PDA is to push a special delimiter dollar, and then nothing is done with that special delimiter throughout all the following transitions until the last transition where we pop the special delimiter dollar from the stack. So this means that for any string that is accepted by this PDA, it should be the case that the stack must have become empty. So which means that to satisfy this constraint, we don't need to do anything as well. At the accepting configuration, the stack always becomes empty for this PDA. If it didn't, then we could easily again convert it to a PDA that would satisfy that criteria and be equivalent to the original PDA. Let's check the final condition, whether it's satisfied or not. The final condition was that every transition must be either a push operation or a pop operation, but not both. Let's check if that's true for every transition that we have in our PDA. The first transition is just a push, no pop, so this is fine. This transition is a push, no pop. The second transition on the loop is a pop but no push. And this finally, the last transition is a pop, not a push. So every transition satisfies that constraint that each transition is either a push or a pop, but not both. Okay, so all those three assumptions are satisfied. This means that we can immediately start applying our conversion algorithm. To simplify our conversion algorithm, we will try to go from the final result and write down the variables as they get necessary. Okay, note that to be able to represent all the strings accepted by such a PDA, we ultimately want the variable A13, where A13 will be able to generate all strings starting at state 1, ending at state 3, assuming both with empty stacks, all strings generated through the computation path from state 1 to state 3. So ultimately we want to generate this variable A13. Let's try to see if we can write down rules corresponding to this variable A13. Remember that we had two cases to consider. This is our state 1, and then our initial transition. We take several transitions, and then we arrive at the state 3 at the end. We want our variable A13 to correspond to every string that we can consume within this computation path from 1 to 3, assuming we start with empty stack at 1 and end with empty stack at the end at the state 3. Now the two cases were, one of them was stack is never empty somewhere in between, and the second one was stack becomes empty case. Let's see if both of these cases are possible. So one case was stack never becomes empty. Stack never completely empty in between here. So we first make a push in here through this transition, epsilon epsilon dollar. We take many further transitions in between, and then we take our final transition where we pop the dollar symbol, and we assume that the stack never becomes empty. Remember that corresponding to this case, stack never becoming empty, we are able to, so the state is 2, this state is also 2. If we can write down the variable corresponding to the strings that are consumed in this path from the state 2 to the state 2 itself, then we can write down, before A22 variable, we can write down the input symbol consumed in here, which is epsilon. So we can write down epsilon in here, and we can write down the input symbol that is consumed with the final transition, which is also epsilon. So corresponding to this case, where in between the path from 1 to 3, state 1 to state 3, stack never becomes empty, we can write down this rule. Let's consider the second case. the second case was stating the assumption that the stack might become empty somewhere in between on this path. However, for this example PDA, it's easy to see that that second case is never possible, because we push our initial delimiter dollar with the first transition and we pop it at the end, and for any of these transitions in here in this path going from the state 2 to the state 2 itself, we can only take this looping transition, and this looping transitions, none of them has to do with our special delimiter dollar. So it cannot be possible that within this path in here we are popping the special delimiter dollar that we had pushed at the beginning. So it's not possible that the stack becomes empty somewhere in between. So we don't even need to consider the second case for this case where we want to generate A13. So stack never empty, other case not possible. Because from 2 to 2 there exists no transition that pops the special delimiter dollar that we have pushed with this initial transition. So our job with A13 is finished. Now let's try to see if we can write down rules corresponding to the variable A2, 2. A2 and 2. We will apply the same idea. So let's try to draw again our figures. So we have our initial state 2 and our target state 2 again corresponding to this variable. We will have our initial transition. Obviously initial transition has to go to 2 again, and then we'll take many other transitions and take our final transition. Okay. Note that to satisfy the constraint that we start with empty stack at 2 and we finish up with an empty stack at 2, it must be the case that this initial transition is a push. So this initial transition must be this one, 0, epsilon, and $0. Okay, and it must be the case that the final transition is a pop, which is this one, 1, 0, epsilon. Okay, and in between here we might be doing any of these, we might be taking any of these transitions. Again, we will consider the two cases that were possible. One was that the stack never becomes empty somewhere in this computation path. Stack never empty in between here, in between this part of the computation path. Let's consider first this case and see how we can write a rule to generate this variable A2, 2. Corresponding to this case, remember we need to, since the stack is never empty in here, it must be the case that we can apply our reasoning to this part of the path as well. So write down our variable to generate the string that is consumed in this part, assuming we start empty stack at 2 in here and ending with empty stack in here. We can do that assumption because we know the stack is never empty in between. So basically generate all such strings that are consumed through this path with empty stack in here, with empty stack in here, because we can forget about the pushed symbol 0 and the pop symbol 0 at the end because they are physically the same symbols. And write down the symbol, the input symbol we consume through this first transition, which is 0 in here, this first 0. And write down the input symbol that we consume with the final transition, which is 1 in here. So this string 0A221 will essentially generate all strings that we can consume through this path assuming that the stack never becomes empty in between this path. Let's try to write down the same. Let's try to write down a rule that corresponds to the second case. For the second case, this is our initial 2. We go to a state, and then the initial transition has to be the same. This is our target state 2. Again, the final transition has to be the same. It has to be a pop, essentially. For the second case, we will assume that the stack has become empty somewhere in between. Let's call it, show it with this state. It's 2. Let's say this is the point where stack has become empty. Stack becomes empty. But recall that for such a case, stack is empty initially at this state 2, and it has become empty somewhere in between, in the middle of the path. Then what we can do is split our variable a22 into 2 parts. The first part, again, we will be able to generate it. We should be able to generate it through our variable a22, because the starting state is 2, the ending state is 2, and at the start the stack is empty. At this ending state 2, the stack is also empty. And for the second part of the path, again, we can generate it through the use of the variable a22 itself again, because stack is empty initially, stack is empty at the end, and we start at variable 2 and end up at the variable 2 as well. So corresponding to this computation path, and this case where the stack becomes empty somewhere in between the computation path, we can write down the following rule that is composed of one part, the initial part of the string, which can be represented with a22 variable, and the second part of the string, again represented with the variable a22. Okay, so these two together handle both of the cases for our for simulating or for finding out all the strings generated through the computation path going from 2 to the target state 2. Finally, one thing that we need to do is remember to handle our base case. For any variable aii, we need to introduce an epsilon rule, basically indicating that to be able to go from a starting state I to a target state I, we don't have to consume anything from the input string. So corresponding to that base case, we will simply introduce an epsilon rule as well. So together, these 4 rules altogether actually give us the context-free grammar that is equivalent to the given input PDA. Now notice that in this context-free grammar, if we since epsilon is simply the empty string, a13 goes to a22, and a22 can generate these 3 rules. So actually, it seems like in order to further simplify this grammar, we can generate the following grammar. A13 is really not necessary because it simply says that A13 corresponds to A22, and the actually useful rules are summarized at A22. So the simplified version of this grammar, using our traditional notation to describe the starting variable with s, it will simply replace this A22 in here. S will give rise to 0s1 corresponding to this first rule, and SS, so since S replaces A22, there's a rule that says S can generate SS, and finally S will generate epsilon. So this will be the context-free grammar that corresponds to, or that is equivalent to the given input PDA.